important to know the backgrounds. Okay, why do we need it? So I want to start looking at this picture first. Take a look. Everyone should know this, okay, outside of circuit 1. So AC signal comes in, transformer, first step. Sometimes you need several different steps of transformers. But anyway, just the transformer stage will convert the AC signal to the voltage range that you need, all right? Second stage is called rectifier. There's the one type of rectifier called half-wave rectifier or full wave rectifier. Or you can say it's a half-bridge rectifier or full-bridge rectifier. So eventually what's happening is for the full-wave rectifier, it's able to, since we haven't learned diodes yet, it's just a one-directional current conduction. But the thing is, if you have a full-bridge rectifier, it's able to flip that negative swing to the top and eventually use the low-pass filter to get rid of these oscillations. So it's converting AC signal to DC. But you can see these little dips and bumps, these are called ripples. They're like a water ripple. They're called voltage ripples. So eventually, your DC voltage should have less ripples, then you have a better quality of the DC voltage power supply. Okay, so we are applying capacitors and resistors that combined to form it's called low pass filter. So only low frequency components can pass, but high frequency will be attenuated. This is something you will learn in the future if you are in the electrical engineering major or minor. But eventually, the goal of this kind of combination is first you have an AC signal, could be from the power outlet or from somewhere else, but eventually you step it down or step it up depending on the application to the range that the peak voltage is very similar to the required DC voltage. Because you can see after the rectifier, the resulted DC has an amplitude very similar to the peak voltage of the AC. Okay, does that make sense? That's why we need a different type of transformer to convert that VM to a reasonable range, so we can rectify it, get a reasonable DC voltage for us. So this is not something new. It happens in your everyday life, and everyone should know this kind of circuit. So you should know like AC voltage comes in, first transformer, okay. Second rectifier, doesn't matter half wave, half bridge, or full wave, or full bridge, doesn't matter. You need a rectifier. So after rectifier, it's going to be low pass filters to convert to remove the ripples as much as possible. Get a very steady state or a very steady DC voltage or stable DC voltage. What's that?
So are you aiming to have less difference in the ripples, or just a total number of ripples should be less?
Oh, ripples should be all gone as much as possible. We don't need the ripples for DC, right? DC voltage is a DC voltage. We hope it to be like 5 volts without any changes. But it's not realistic. So there will be ripples because it's converted from a sine wave. But by using these low pass filters, we are able to remove a lot of ripples from it. So that's why when you are probing your DC voltage through a microscope or oscilloscope, you can see a pretty straight line. But if you zoom in, there will be noises or ripples. That's pretty good. It's good enough to drive all these DC devices. So that's from AC to DC. Okay, this happens everywhere. Little adapter, the little charger for the phone. You see the little charger for the phone, right? Everyone has it. So that little plug, even though it's very small, but if you open it up, you can see little transformers inside. So it's converting that 110 volts AC to a lower AC voltage and then rectifies it. So it has rectifier in it, has transformers in it, and eventually has voltage regulators, which means the rectifier output is probably giving, for example, 9 volts DC, and you use the voltage regulator to regulate it to 5 volts, which is providing the 5 volts power supply to the USB. Okay, that's how that works. It happens everywhere. Everybody should know this, okay? So this is one very typical or traditional way that we rectify our power supply for our appliance at home. There's another way, happens getting very popular recently, okay? So you probably hear somebody leave totally off the grid. Okay, what does that mean? So they're not connecting their house to the power plant. Okay, so they're not getting any AC power from the power plant. But why they are still able to get 110 volts out of the outlet of the plugs, in their house? It's totally off the grid. They didn't connect their power system to the grid at all. So they use solar panels. Solar panels that receive the solar energy. These are semiconductor materials, and which is able to accumulate the charges to the two terminals and forming DC voltage. What's that?
So when we're talking about like generators, you said it's like spins. That's what creates a wave. Is it the same thing here? Like
No.
heat makes things spin?
It's totally different. Okay, so there's no AC power from the power plant. That for the power plant, like for example turbine, right? All these generators, they rotate, and the rotor inside cut through that magnetic field, and because of physics, right? When the metal cuts through the magnetic field, it generates current in the metal. So that's how we got AC voltage, because it's spinning. So that's why it's coming up and down. That's the AC voltage generated by power plant. So the power plant sends that AC voltage to the house, and you are getting 110 volts AC voltage over there. So that's what we have. So we have to convert it. We have to step it down first, because most of the devices, laptops, are 20 volts DC. So we have to step it down to, for example, 30 volts AC, and then maybe 20 volts AC. I don't know, but somewhere around 20 volts. Okay, out of transformer. The transformer connect to the rectifier, so rectifies it to DC voltage, 20 volts or 22 volts, doesn't matter. Should be a little bit higher, because whenever you are regulating it to stabilize it to 20 volts exactly, you are getting some loss. So 22 volts DC, for example, after the rectifier, and then you regulate it to 20 volts exactly for your laptops. Eventually, you are getting 20 volts, very stable 20 volts, not damaging all the sensitive electronics inside. So that's what the little box, your little adapter, a little box that you got your laptop, the manufacturer sent to you when you got your laptop, right? So that's adapter. What the adapter does, it does the transformer step it down, rectification, and regulation. So that's how you can get 20 volts stable. That's that path, right? So for example, if you don't connect your house to the grid, so eventually you are getting all the energy from the solar panel. Solar panels are accumulating charges. There's no generator. So what's happening is the sunshine hits the solar panel. So inside it accumulates charges across the two terminals. So eventually it's getting DC voltages. And that DC voltage is purely just DC, even though sometimes it's not stable, but it's not sine wave. However, all our devices, like our adapters, they are designed for that 110 AC voltage from the power plant. Because that's how that's designed, right? So in that case, we have to use the equipment, it's called inverter, to convert the DC voltage back to the AC voltage, 110 volts, and send it to all the sockets or outlets in the house. That's how that works. That's the two different paths or strategies to power up your house or RV. Okay, you can see people are powering up their RV totally just from solar panels. And you do need an inverter, which is the equipment to convert that DC to 110 volts AC in order to let your old appliance in the house to use it. Okay, and also there's another charge control, which is able to charge up the batteries. Sometimes the RVs, they have a battery to store the voltage, or stabilize the voltage to 12 volts, because a lot of devices in the RVs are using 12 volts as the input. So that's the two main power strategies most recently in a modern society. So another thing we need to know, which is called AC motor, and we'll cover something about this in homework 11, because homework 11 is everything about three-phase voltages. So now we haven't covered that yet, but it's okay. So we'll get there next week, hopefully. Wednesday or Friday, we'll do the lectures and homework assignments for homework 11, which is the last one. Yeah, done. Okay, so why we care about three-phase voltages? It's very, very simple concept. Okay, so there might be one problem on three-phase voltages in final exam. So AC motors, some of the AC motors, induction motors, they require three phases of voltages to drive it. If you only have one phase, it's called stator, right? So the stator have three different coils, so it's able to receive three different phases of voltage, AC voltage, and that AC voltage will induce the magnetic field, and then creating a current in that rotor, and which is generating a opposing magnetic field. So what's that doing is pulling that motor away from that stator, which is these ones, the stator, these ones, is pulling this rotor inside away from the stators, so it spins. Okay, so whenever it spins to here, then you activate it using a different phase, and then it starts pulling it towards the other direction, towards even forward, right? And then you activate this one, then it's generating another magnetic field, and then pulls it to the next. So that's how it's doing that kind of relay, keep the rotor rotating inside the motor continuously. So that's why you need the three phases. Sometimes you'll see there's a two-phase. You can do it two-phase, but you can imagine that three phases will be definitely more efficient than two-phase, right? Because you have less sort of gaps in the middle, and same for one phase. So this is one of the most important applications for three-phase. You have heard about three-phase power supply a lot, but why do we need it? So this is one of the most important applications for three-phase voltage power supply. Okay, why? It's more efficient. Okay, and also our three-phase induction motor requires a three-phase voltage input. That's the two main reasons for that. Okay, another thing about it, if you have three phases, you can imagine, just consider the power supply efficiency. If the three phases are being applied to a load, you can see it's not really, so when sound wave comes up, it will go down at some point. But if you have three phases, so before it goes down too much, you get another peak comes in. So eventually, in general, overall, it's providing more power to the load. So eventually, it's just more efficient. Okay, whenever you have a heavy load, usually it's for example the shopping mall or factory, which have a lot of appliance or equipment requires a high power, you need a three-phase power supply. But in your house, usually something drive your fridge and other things, they are just like one phase AC, 110. So these are not three-phase power supplies. Okay, just some general big picture about why we care about AC voltage in three phases and induction motors. And now let's come back to our homework 10. So now if you look at the generator, it makes more sense. It's not something like magical anymore. You know, it's serving for a certain purpose, right? It's useful. And you have it in your adapter, phone charger as well. I already went through the first problem here. This is exactly the first one in homework 10. I did it a long time ago, I think, probably 3 or 4 lectures before. Don't want to take too much time over here, but I already wrote down all the equations in that notes. Refer to that notes, okay? I didn't cover this one. Problem number 2, okay? Have you used the solar panel before? It's very interesting. It's just a photo to electrical converter. That's what you want to consider it. And it's really interesting. I did an experiment, probably couldn't even believe. So a solar panel receives light signal and convert it to electricity, right? So if you get a stronger light, you get a stronger analog voltage output. And I have used a solar panel as a receiver. And I used for example, I'm playing a music from my phone, and I amplified that music sound, and you directly connect that analog audio signal to a LED, so the LED will blink depending on the audio signal's intensity versus time, and that blink will get the light signal received by the little solar panel I bought from Amazon. So the solar panel receives that light signal. There's nothing connected, okay? No hardware connected. Just a blinking LED of the audio signal of the song, and received by the little solar panel. And the solar panel converts that blinking light signal into an analog voltage, and I use the audio amplifier amplifies it, and I can play the music using the solar panel receives a blinking LED. It's a really interesting experiment to play with. So there's no connection, it's just like a solar panel and now blinking LED, and it plays the music from here to here. All right, so yeah, what's that?
Do like warmer colors receive better data from like solar
It could be,
panels?
yeah.
Or does that not really matter?
I think shorter wavelength, which means colder color, has a stronger energy. So it should have a better response, I think. But depending on the semiconductor material, you design it for a certain bandwidth, right? It could only receive IR signal, could only receive visible, could only receive UV, depending on the bandwidth, the design of material. Yeah. Okay, so this one, N2, N1. You can try that kind of experiment with your kids in the future. So fun to play with. V1, V2. It's asking for ZAB, okay, the impedance of impedance across its two terminals. V2, V1. A little dot terminal follows that sign convention. So the sign convention, I mentioned it probably last week. Let's just remember it, put on the notes, the cheat sheet for the final exam, because there's a problem on transformers, okay? So it is, because we know that this is always true, V1 over N1 equals V2 over N2. That's always true. I1 N1 equals I2 N2. Okay, but depending on the polarity and the dot, where you have the dot, you may have V1 over N1 equals plus minus V2 over N2. I1 N1 equals plus minus N2 I2 N2. But one is positive, one is negative. I think the description from the tutorial tells you that if the voltages, like for the voltages, are both positive or negative at the dot, then V1 over N1 equals V2 over N2. Just make it short, okay? Let's see. Is V1 and N1, V1 and V2 both positive or negative at the dot? Yes, it's both positive at the dot, right? Okay? So it should be this. No negative sign in front of it. But for the current, it's opposite. It's one comes in, one how to say that? One current goes into, and one goes out of the dot, then it's I1 N1 equals I2 N2. So one comes in, one goes out. Then it's positive, right? Just put this on the cheat sheet if you couldn't remember it. Let's see. I1 is going that way, okay? So if it's going that way, you consider that I1 is going out of the dot. Okay? What about I2? I2 is this, right? I2. It's getting into the dot. Okay? I1 is getting out from the dot. I2 is getting into the dot. So it's also positive over here. Right? That's why we can list all the equations. list all the equations. So we got a VAB here, because ZAB is the impedance of these two terminals, but also we got a VAB as well. So VAB equals what? VAB. Let's say ZAB first. Do ZAB because it contains VAB in there. So ZAB equals, ZAB means the impedance you look into these two terminals. If you look into these two terminals, you see an impedance. Okay, it's asking you for that value or the expression for that impedance. So ZAB equals VAB divided by IAB, right? So which is the current getting into the network over here. So this is just one current, which is the IAB. So that current equals what? You got two branches, right? Okay. So VAB is the overall voltage divided by the overall current, which is the two branch currents. Will give you the ZAB, give you ZAB here. So VAB divided by these two currents, according to KCL, you have I2, I1 plus I2 for these two branches. And VAB is what? If you look at it, VAB is exactly V2. Right? Okay? And V2 plus V1, you can see it's plus minus like two batteries stacking onto each other, right? It's like V1, V2. So overall it's V1 plus V2, okay? That's the overall voltage, V1 plus V2 over here across these two terminals, okay? And you can see there's only one current flowing out and eventually reaches ZL. So I1 times ZL will be the voltage across ZL, which is exactly V1 plus V2. So V1 plus V2 equals what? I1 times ZL, and ZL is given. What is ZL here? You don't need to know. Just the ZL is given, okay? What else do we need to know? It's a transformer, right? Even though it looks weird, but we know that they are both positive over here. So V1 over N1 equals V2 over N2. And we also know that I1 N1 equals I2 N2. That's given. Okay, these are all the equations we need to know to find out ZAB. Why? Because just use this equation. Here, substitute VAB. Okay? And I2 can be replaced by, I'll write it down. ZAB equals to V2 over I1 plus what? Plus this guy. I2 is here. It's I1 N1 over N2. Okay? So what is V2? V2 is substitute V1 using this equation. You got another paper. So V1 equals V2 over N2 times N1, right? So plug it back in here. We're getting V2 N2 times N1 plus V2 equals I1 times ZL. So we know that V2 equals I1 ZL over 1 plus N1 over N2. All right, done. V2 substitute in here. So you only have I1 in the expression. So directly cancel I1 on the top and bottom, so I can get a ZAB without any variable in it, just the n's. N's are given. Consider n's are given. Number of turns of the coil. Okay. I'll let you do the remaining. It's just one more step. Very simple. You'll figure out later. Right? Not right now probably, but you'll figure out later. It's really simple, just one more step. Okay, I already tell you what to do. I have to cover another thing you probably don't know. Okay, so for part B, it's asking you to change the polarity of the dot, change the location of the dot. So for part B, you want to use this equation instead of the previous one, but it's still the same strategy to find it out. The answer is V1 over N1 becomes negative V2 over N2, and also I1 N1 becomes negative I2 N2. All right. Just using this stat for part 2. Try to find out the answer. For next ones, let me see if there's anything you need to know. Okay. V equals 120 cosine omega t. I think it's nicer to have a problem number here for you guys. 10.1 minus 45 degrees voltage, and I equals 25 cosine omega t plus 15 degrees amp. So it's asking for the reactive power. Reactive power. Because we know the average power, right? So average power or real power. Let's do both. What's the reactive power? It's Vm Im over 2 times sine and phase shift, which is minus 45 minus 15. Average power Vm times Im over 2 cosine minus 45 minus 15. That's it. All right. So if you are getting, if I'm drawing a box, 2 boxes here, like A and B, and I'm labeling the polarity of the voltage like this and current, so that's important. Okay, current direction like this. It's from A to B, with that current. So this current is this current. Okay, and you are using that current to calculate the reactive power, but eventually you are getting a positive number. Okay, what does that mean? If you got a positive reactive power, this is the current direction you use, and this is the voltage direction you use, and this is the current direction you use. And eventually you calculate a positive reactive power. What does that mean? That means B is absorbing. So the power is actually delivering in that direction. If you use this direction of the current and you find out the positive reactive power, so which means it's absorbing. Okay, this is the current direction is the power is being delivered in that direction. Okay, so B is absorbing, A is delivering. Okay, so this will help you solve all the problems until 10.7. Only one thing you need to know, I think, because we already covered that. Remember, we spent 2 lectures to cover the general cases for these parallel or series guys, right? Remember? Like C and DJ, that's what we did, right? So you should be very comfortable with this type of problems. So, but the thing is, it asks for something else, which is unimportant, but you just need to know how to calculate it. I'm not going to derive it over here. So it's asking for the peak. I already did it last time. But just want to remind you about that. So Px is called instantaneous power. It's asking for the peak instantaneous power, which equals, it just directly use the equation, okay? So P plus P squared plus Q squared. You know how to calculate average power and reactive power. I just put it together like this. And P minimum equals P minus P squared plus Q squared, okay? So whenever it's delivering the maximum, which means it absorbs the minimum, like I said last time, because I'll just read the problem for you, okay? The question, part A. What's the peak value of the instantaneous power delivered by the source? Peak value of delivered by source. Peak value delivered by source. Use this one to calculate it, right? For part B, it's asking for peak value absorbed by the source. Right? Absorbed by the source. Then you use this equation to calculate it. Because whenever it absorbs the minimum, whenever it delivers a minimum, it absorbs the maximum. Okay, that's how you analyze it. When it delivers the minimum, it absorbs the maximum. It's the power going back and forth from the reactive load. Average power, you know how to do that easily, right? Average power, how to calculate it. Because it's in parallel, right? So we just focus on the resistor. We have two methods, but let's just focus on the resistor. Average power. Real power, I have done this for so many times. Average power, right? Average power. How? Parallel, so voltage is not changing. Okay? So what's a VM? This guy. What's IM? It's VG. Yeah, just over resistor, right? Square. Yeah? It's VM times IM divided 2, right? What's the cosine theta for resistor? 1. So it's basically for average power, P equals this guy, which is VG squared over 2C, right? Very simple. So this is method 1. We just focus on the resistor, depending on which one's easier. Okay, it's a series or parallel, depending on which is easier. Just use the easier one. You can either focus on the resistor or focus on the whole impedance. Either way. Any question on this? Definitely, this will be on the final. Okay, this is very important. The main thing we want to focus on homework 10. The main part to cover. We always care about the average power as the main power being consumed by the load. The reactive power is just going back and forth. It's not really getting consumed. We also care about it because we want to get rid of it. But the real power is something really getting consumed, right? So the thing is, if you have a higher reactive power, you want to get rid of it. But a lot of times, people will connect their inductive load to the circuit. So there will be some inductive kind of power being happening in the circuit. So in that case, you just need your source will have a heavier load. It just has to deliver more power to satisfy that thing that consumes real power, because it sends like 100 watts, for example, and 20% of them are getting stored in the inductive load. So eventually, only 80% delivered to the resistive load. Okay, it's not using it; it's just storing it. But storing it and not using it, we eventually send it back. So it's just, it's not wasting anything, but just creating a lot of load for the source. Okay, power factor, we talk about this, right? Several ways to get the power factor. Remember, average power equals what? VM, IM, the peak magnitude voltage divided by 2, because divided by square root of 2, divided by square root of 2, these are VRMS values, cosine, theta V minus theta I. And this is called the power factor, and it's always between 1 and 0, right? and you want your power factor to be as close to 1 as much as possible, so it's better or higher efficiency, is achieved if you got a 1 power factor. So which is getting a 1 power factor? What kind of device is getting a one power factor? A resistive load, right? Remember, when we are doing a resistive load, we are calculating the resistor's power, real power. The cosine, the V and I phase shift is 0 degrees, which is giving you cosine 0, which is 1. So this part becomes 1. So your power factor is 1 for resistors. Okay, that's the ideal case. But if you have the reality is you have inductive loads or capacitive loads, so your power factor won't be 1. Okay, but you want to reduce it. You want to increase it to 1 as much as possible. Also, what are the other ways to calculate power factor? Power factor also equals what? Also equals what? Average power divided by square, sorry. Okay, there are 2 different ways to calculate power factor. And this also equals what? So S is called apparent power.
Is the power factor material property of the component, or?
It's calculated by the impedance. It's an impedance phase shift. It's a cosine material, yes, because in different inductors will give you a different phase shift, right? Yes, but eventually just the V and I phase shift, depending on the impedance. So this angle is what? Remember, we talked about this a little bit, right? So by knowing this back and forth, you know where this comes from. Will make you confident for the final exam or in the future dealing with this type of problems. So what is this? This is impedance angle, right? Impedance angle. So we have done this several times in the class in the past. You can refer back to the notes. Why is the impedance angle? Okay. But the difference, the phase difference from the voltage and current, in between the voltage and current, is basically impedance phase. You want me to do this again? Voltage, phase, I, phase. Remember? What is this? V over I is what? Impedance. Angle what? 5-star service, okay? Repeating. You guys are so ready for the Thanksgiving break, right? All right. 8 more minutes. So V, phasor V, phasor I, division, phasor Z, phasor impedance. So phasor impedance has an angle here. So the angle difference is actually basically the angle of the impedance is the angle of the phase difference between V and I, which is basically here. So if you see theta V minus theta I, it's basically the impedance angle. Okay? Knowing that will be very helpful. And then problem 10.17. 10.17. It's just exactly the same problem. It's just repeating. Even not changing the number. Oh, just changing the VM, but nothing else. Same circuit. Even the resistor value is the same. Anything we need to do here? Apparent power, okay? Told you, apparent power. How to calculate apparent power? P squared plus Q squared square root, right? Find the power factor. Power factor, how to calculate power factor? Repeating. Okay. Oh, 10.41 is a bit trickier. 10.41. Is it due Monday? Right? Okay. 10.41. Probably haven't seen that problem yet. Should I do this or no? Probably won't be helpful. Don't want to rush. 6 more minutes, won't be able to finish it. Just telling you that if there's no load connect to a circuit, let me draw this for you. No load connect the circuits. And then it shows a voltage. Here is 360 and 0 degrees. Sorry, 360 volts. RMS. If you see RMS, which means this is the right RMS value, you don't have to divide it by square root 2 anymore. So it's not peak value, it's the right RMS, so right divided by square root 2. Okay. So what does this tell you? I'll just stop here after I finish this comment about this first statement here. Yeah, but I mean, it's telling you that, hey, I got a circuit. When there's no load, I read the voltage as this. Is that something familiar to you guys? So in Thevenin's equivalent, when we try to find out the VTH, what we do? We remove the load and find out the terminal voltage. So we know the Thevenin voltage, right? So I tell you, when there's no load, you got a voltage like this. So what is this voltage? That's a Thevenin voltage. So if you convert, for example, now, even though this original circuit doesn't look like this, but we can convert it to the Thevenin's equivalent voltage. So we know the Thevenin's voltage will be this, right? So we do it here. Why I keep doing that? RMS. And ZTH. Can we do this? Yeah. So we directly convert it to Thevenin's equivalent. So we know there's a resistor in series with the source, and the source voltage is this guy, the terminal voltage. And then it tells you, because it's equivalent, we don't even need to know what the original circuit looks like. It's okay. So now we know that the circuit has a Thevenin's equivalent voltage, had a what's that called? RTH or ZTH, whatever. You connect in series with it. And then it tells you that if I connect a 100 ohms resistor, the voltage here becomes 180 minus J60 volts. It could be confusing, like why the voltage here is changing, since now you have a load, right? That's why it's changing. If you don't have a load, it's gonna be this voltage. If you connect a load, the voltage shows this, right? Okay. So now it's asking you a bunch of questions. Is this helpful? If it gives you 100 ohms, it shows a different voltage. Why is this helpful? Even though we are not using the 100 ohms resistor in the future, but why is this helpful? What can you do by using these two parameters given to you? Yeah, so now you know this voltage here, you know the resistance here. So what you can do is to find out the current, right? You find the current here as well as the same current. So you can eventually find out ZTH. Okay, so now you got an equivalent circuit. ZTH, you can calculate it. You can get an equivalent circuit out of it. So you can use equivalent circuit to do analysis for the remaining. So for example, I got ZTH to be A plus BJ, okay, A plus BJ. And it's asking you like what kind of load you want to connect to here to achieve the maximum power, power consumption or maximum power deliver or power transfer. Sorry, max power transfer to the load. What is this should be? So remember in the past when we are trying to do a maximum power transfer, we let the load resistor to be equal to the RTH. Remember that's what we did a long time ago? Okay, so now it's not, you don't want to directly match it. So what you want to do is have A minus BJ has a conjugate of that ZTH. So if you add together, this inductive part will be gone. So you are getting maximum power transfer because you don't have reactive power consumption. Okay? And your real power, the resistive part is still the same, which is still the same as the DC voltages, right? As the DC circuits we deal with. But the reactive part is gone. Okay, this is what you want to use. So calculate this from here, and then find out the maximum to be this. And it also asks you to form a load to be put in here using different values of capacitance and resistors. Very simple. So I think by now I think we have covered every single problem in homework 10. You should good to go. So please work on it during the weekends, and so on Monday we'll start working on 3-phase voltages. Okay, see you on Monday.